Hello everybody. So in this video we're going to start the discussion on the details of calculating the loss coefficient for the different causes of minor losses. In this video we're going to discuss the first two causes, and then in the next video we'll discuss the last two. So for the first source of minor losses is the pipe inlets and exits, and this is the pipe inlet, something that we discussed in details in the beginning of this chapter when we were discussing the entrance region and the fully developed flow, and how the flow develops from a flow with regular velocity all over the whole diameter into, and gradually develops to be the fully developed flow. So and we showed that this leads to high pressure losses. So this is one of the things, of course, higher than the pressure losses in the pipe itself. This is one cause, and there is another cause that we will discuss shortly. But anyway, so we have here in this table, and it's important to be familiar with these tables, because in this table there is a title here. It's not like a big font title, but it's the title. It's written in another color. And this tells us what these coefficients are about. So these are all about the pipe inlet. So we have different shapes of pipe inlets. We have what's called the re-entrant pipe inlet, and this is what you would have if you are fitting a tap to, let's say, a tank or something. So you drill a hole, and then you put the tap inside, and you fit it from the other side with a nut or something. So there is part of the pipe that is going inside the fluid on the other side, and this is what we call the re-entrant flow. For this case, we have KL is 0.8, and of course this is for the cases of or based on these conditions. And this is something you need to keep in mind, that what we have here in the textbook are just examples. It's not all the cases. There might be other textbooks or other references that have detailed information about various cases of pipe inlets or pipe exits or other things that we will discuss later. So this is something you need to have in your mind. So it's not covering everything. So the case that we have here is for thickness of the pipe to be much less than its diameter, and to have the entering part here to be almost 10% of the diameter of the pipe. So in this case, KL is 0.8. There is a case of the sharp-edged pipes. So this is a case where the pipe is welded to the container, or the place where the fluid is flowing from. And we have two cases. Either the pipe has a sharp edge, it means that the angle here is 90 degrees, or it has a rounded edge. So this is not a very sharp edge as it's here. It's not like a right angle. It goes from here to there over a radius of curvature, which is this small r. The simple logic tells us that the sharp edge will have more losses than the rounded edge. The flow through rounded edge is more smoother than flow through sharp edges. So for sharp edges, KL is 0.5, and for rounded edges we have two values of R and D, or R over D, and it's 0.03 or 0.012. Of course, these are just examples. We have a chart that gives us more information. So here you have R over R, which is this lowercase r over over D, over this diameter. So as the radius of curvature increases, the loss coefficient decreases, which is very, very expected. And we'll discuss this also in the next slide in more details. But here, yeah, let's check for R over D equals almost 0.2. It's here. You see, it's almost asymptotes here. Like the value doesn't change that much. So it's around 0.03. If it's, let's say, 0.1, KL is around 0.12. So you can just use the chart if you want. So this is the case of the pipe inlets. For the pipe exit, we have, for all the cases, and I think this is also expected, that the exit of the flow doesn't affect the pressure drop that much because the fluid is already leaving. So it doesn't have that much effect as in case of the pipe inlet. So for the pipe exit, of course, there is some disturbance in the flow, and it's not flowing as it used to be through the whole pipe. And this leads to more losses, but it's not as significant as here. I mean, the shape of the pipe is not as significant as here. So for these cases, KL is alpha, and alpha is 1.05 for turbulent flow and 2 for laminar flow. Just to understand how why the sharp-edged pipes led to more losses, we need to understand how fluids flow. So fluids cannot flow or take sharp turns. It cannot go or move forward and then directly move 90 degrees to the right. It has to go through a curvature. And this is something I think you have seen this many times. For example, the case that we saw before for the tank that discharges the fluid. The fluid didn't flow like this. It went through a radius of curvature. So this is how fluids flow. So if it has a sharp edge, then the fluid will go through a radius of curvature like this. And there will be a region here and region here that's called separated flow. This is a dead zone. The fluid doesn't flow through these two regions. It's just squeezed in this small area inside that we call the vena contracta. So what happens if you take a look on these two lines? One of them represents the velocity and the pressure. This is the pressure, and this is the summation of the velocity and the pressure. So you'd see here that once the fluid starts to enter the pipe, the velocity will increase. The velocity here is high. I mean, the energy of the fluid is still the sum is the same, but the component due to the velocity is very high. I mean, in the beginning it's mainly pressure. Here it's like a big tank, so the velocity is almost zero. So the energy of the fluid here is mainly due to the pressure. Once it goes here, the velocity starts to increase and the pressure will decrease, which is something we expect. The height is the same, so the pressure will decrease when the velocity increases, and this will keep going until the vena contracta, where the pressure will reach the minimum value and the velocity will reach the maximum value. This is the velocity and this is the pressure. After the vena contracta, the velocity will decrease a little bit, and because it's now occupying more area, so it's going to be less, and the pressure will increase. But this sudden change in the flow velocity from large area to small area to larger area again, or bigger area, this leads to some losses. That's why we have here the sum of the energy after the vena contracta is less than the sum of energy before the vena contracta. So this is the losses. So when we have a round edged pipes or inlets, this region that is separated flow, or the dead region where the fluid is not flowing through, becomes less, and the vena contracta area becomes more, so the losses will decrease. So this is why the round edged pipes are or entrances are or cause less losses than the sharp edge. The second case or cause of minor losses is expansions and contraction. By these two terms, we mean that the fluid is flowing through a pipe with a specific diameter, and then the diameter changes to larger or smaller diameter. So if the fluid flows through a small diameter to a larger diameter, then we call it expansion. If it goes from large diameter to small diameter, we call it contraction. The expansion or contraction can happen suddenly, meaning that the diameter will suddenly change from, it's a step change in the diameter from the small diameter to large diameter, or the opposite case, from the large diameter to small diameter, or it can be gradual. So it goes from this small diameter to large diameter over some distance, which is what we have here. So this is why we have the sudden expansion and contraction, and we have the gradual expansion and contraction. So these are two different cases, and of course we expect the losses in this case would be less because it's gradual. Anything that happens gradually leads to less losses than what happens suddenly. So for both cases, for sudden expansion, for sudden expansion, KL is calculated from this relation. Okay, so it is KL alpha times 1 minus D over D all power 2, or area over area all power 2. So we just substitute in the equation, and by the knowledge of the two diameters we can simply find the loss coefficient. There is one interesting thing here, which is in case of expansion, let's say we have a small diameter that is, or the large diameter is much larger than the smaller diameter. In this case, this term will be zero, almost zero, and then KL is going to be equal to alpha, which is this case. Okay, so the sudden expansion or the pipe exit can be considered as a special case of the sudden expansion, where we have a large ratio of areas. For the sudden contraction, we have this chart here. So it depends on the ratio of D square over D square, and then based on this we can find the value of KL. Anyways, this is the way we get the loss coefficient for sudden expansion and contraction. If it's gradual expansion and contraction, we do this, or we need to include two parameters: the ratio of the diameters and the angle by which the diameter is increasing or decreasing. So we have here theta, which is this angle, and theta is double this angle. And if you look at this angle here, this is half theta. So if its theta is 20, then this angle is 10. Okay, and again we have just limited data here. So there might be different angles, there might be different values of D over D. So in this case, you need to find another textbook or reference for this. So this textbook is just giving some examples. So it depends on for theta of 20, it depends on the ratio of D over D. And this is what based on which we can find KL. For the contraction, it's independent on D over D. It just depends on the theta, the value of theta. So these are the values of KL for different thetas. Okay, so this is the case. One more detail here. It's important that we know that the loss coefficient is used with or will be substituted in the equation KL times U square over 2G. So we have two velocities in this case. We have the velocity in the smaller area and the small area, and the velocity in the large area. So which one should we substitute with? Based on the figure and based on, before the figure, it's important. This is why it's important to read the title. So in the title, it's saying that the sudden expansion and contraction based on the velocity in the smaller diameter pipe. So this has to be calculated used with the velocity in this area. And again, this confirms what I was just telling you, that you might have a case where this diameter is very big, so the velocity here is 0. So you cannot substitute with K times 0, so it's going to be 0. So that's why all these loss coefficients are calculated based on the velocity in the small areas. Okay, so this is a very important point to note. And also you can see here that this is the only velocity that we have in the figure. So even from the figure you can tell that this is the one that we are interested in. So I'm going to stop here, and inshallah in the next video we're going to discuss the rest of the loss coefficients for the rest of the result. So I'll see you then, inshallah. Goodbye.